pH sketches shows a gradual change in pH as the process of neutralization titration continues. This is a general sketch. So you can see the pH becomes sharply increasing at the neutralization point. It depends upon the acid, how much strong acid we are using, and how much strong alkali is being formed to the shape of the graph. Acid neutralization and forming alkali. So this is a general template. You have to copy this.
Okay.
This is a titration reaction, and notice the range in which neutralization is taking place. So looking at the graph, looking at the theory, that is the point where they select a suitable indicator.
I've copied.
To the pH range. From this graph, the pH range will determine the suitable indicator. You have to update the sketch.
Okay. I've copied.
Now, we always look for the vertical section. The indicator must change during the vertical portion of the curve. Different indicators are used. For example, in this example, we are using a strong acid because we are coming from around 2 plus number and going up to 12, a bit lower than 12. So we are using phenolphthalein. So phenolphthalein will be suitable. In the example, the only suitable indicator is phenolphthalein because methyl orange will not be active in the range we are looking for. So there are acid-base titration between strong acid versus strong base, weak acid versus strong alkali, strong acid versus weak base, and weak acid versus weak base. So this is a general table, and we are having this knowledge from AS chemistry, that when we design a titration, it is important to see what is the pair. For example, we are having alkali 0.1 molar and added to 0.1 molar acid. So when you make them neutral, a strong acid versus strong base, look at the graph. The graph is starting from a very low value because it's a strong acid. It also reaching a big number because it is a strong base. In this case, the vertical section is so big that virtually every indicator will be fit here. Now, if we the strong acid working weak alkali, the graph will begin to move around 10 and 11. So methyl orange will be more suitable. If we are using weak acid versus strong base, the graph will be starting from a bigger number because it's a weak acid like carboxylic acid. But the graph will take a higher approach because alkali is a strong. Again, now this time phenolphthalein is better because it is capturing the vertical section. Interestingly, when you have a weak acid and a weak alkali, technically there is no sharp vertical section. So theoretically, no indicator is perfect. Other pH curves are like when you are using some salts and you are using combined equations. This is a case which I hope you remember that apart from pure acid and pure bases, there are some salts which behave like acids, like alkaline salts, acidic salt. So there are also compounds which behave like acids and alkali. For them, the graph can vary. Again, the vertical section should be considered. The pH curves of phosphoric acid and other complicated acids are there. The main point is there why they are having why there are 2 or 3 vertical positions. It means there are 2-3 neutralizations. This is a case when an acid does not become neutral in the first step. It partially neutralizes and converts to another acid, then another acid, and then it neutralizes. This is a case of multiple neutralizations in one. Now we come to our main topic. This is the key topic, the main topic of this chapter. Every chapter has a core topic, like energetics, lattice enthalpy is the main topic. And when you talk about electrochemistry, then electrochemical cell is the core topic. Core topic means that the whole chapter, within the whole chapter, examiner majority time focus on this in paper. So this is the core topic.
Okay.
For solutions, you have to give the heading and mark it core topic.
Okay. I've copied.
Now, the idea of buffer is there in our normal proverbial language. Buffer is a zone where you can actually retreat. It is a no man land. It is a neutral position. Buffer solutions are those which resist changes in pH when small quantities of acid or alkali are added. The one of the best example which actually taught every scientist how they work is our blood. We take number of food items and we take different medicines also. Some medicines have slightly acidic environment, some also have a basic. Our stomach contains a proper strong acid. So nature has managed a remarkable system to maintain the pH of our blood. That solution, the blood, is capable of resisting changes in pH. And this is a very interesting example, but this is actually how we can link chemistry, because many people do not find chemistry that much linking. Even though all teachers tell, even I tell my student that that chemistry is actually not linking to chemistry for many people. Why? Because chemistry is not linking with our life. Chemistry is the life, because organic, the word organic is the biggest terminology used for life. So we all are organic. Nowadays, people are talking about chat GPT, artificial intelligence, and a lot of movies are made on this idea that there will be a time when the reality, organic systems will have a conflict with the electronic systems. So humans studied blood, and blood is supposed to be the life-sustaining liquid we have. This solution has a remarkable capability of fighting against the intruders, not talking about the antibiotics, etc., talking about the pH. Actually, pH is something which is critical for the life sustenance. Many compounds which we use to kill these small insects like cockroaches, etc., they are capable of changing the pH. Now we have a very interesting example. Some people have a taste of taking those chewing gums and mouth fresheners, which temporarily changes the pH of the saliva. Now, our saliva has a very very distinct pH. When the food items reach the stomach has a different pH. When you go forward, and
Yes.
obviously bio, so you know the significance of pH. Now nature maintain the pH in blood because a big change in pH in blood can be lethal. So we got this point that pH changes in pH are resisted by some solutions. Such solutions are called buffer solution. You have to copy this.
Okay. I've copied.
There are two types of buffer. One, weak acid plus its soluble salt. Second, weak alkali plus its soluble salt. You have to copy this.
Okay. I've copied.
This is a case acidic buffer made from a weak acid like ethanoic acid and its sodium or potassium salt like sodium ethanoate. Alkaline buffer example, a weak base like ammonia. Ammonia is a selection because ammonia is an alkali. And obviously you remember that all bases are not alkalis. Ammonium chloride is the salt. You have to copy these examples.
Okay. I've copied.
Buffering biological systems, this is a common example, and standardizing pH meters, maintaining the pH of shampoos. Shampoos example is looking a bit rare for many people, but this is a very important example. And buffering is needed so they do not change the pH of the users here. All good cosmetics are have a marking on it, chemically treated or medically treated. So this is a commitment there that they won't change the pH, because changing the pH of the skin or anything related to those cosmetic interface can cause severe problems. Because as I mentioned, that pH is actually the concentration balance of H plus and OH minus. Many poisons, they actually change the pH irreversibly, that causing severe damage. Now you have to copy this screen.
Okay. This topic is interesting.
Many people like it, and in the world, many people are now diverting from MBBS and BDS, and many people now know that this is also a huge industry. And just like an off the record thing, that many people now feel that medical is too long, and no doubt medical is long, but the prestige is there. But the chemical industry related to biological stuff, now the industry has grown a lot. And very interestingly, if you, whenever you have a time and you see the numbers, cosmetic industry is huge. It is so huge that perhaps I think many big industries have no competition with it, because here you can you have some emotional attachment with the people, that people want to have some cosmetic changes. Now, apart from cosmetics and apart from general, there is a very important research for pharmaceutical industry. They have to make medicines, and the medicines have to go in the body. Some medicines are taken through mouth, they reach the stomach, intestine, and then they reach the blood. So they have to go through multiple pH. Now, this is the challenge for the manufacturer to maintain the maintain the medicine so that it does not decompose before the target. There are some medicines which are designed to decompose in the mouth. It means they follow the saliva pH, but some do not. They reach the stomach, HCl is there, high acid pH, that is all there. Some are designed to go forward, and that is why, this is the reason some medicines are not taken from the mouth, they are injected in the blood, IV or IM, because they can't sustain the pH changing environment. So this is where the biological uses come. And there was a topic which was very famous on its time. In 2007, it was introduced, and then in 2016, they have withdrawn it. The syllabus changes. But that topic was very interesting for many new students. That the topic name was drug delivery. Unfortunately, the word drug is used in some other sense, but drug delivery is a very important technique. And after some syllabus reviews, it was taken out that how drugs, medicines are taken in our body, and they have to maintain the pH changes. If the pH of blood varies by 0.5, it can lead to unconsciousness and coma. Most enzymes work best at particular pH. These are all biological details, and none of the details are needed apart from only the connection. That pH is important for majority of the living system reactions. Other uses,
Yes.
many household and cosmetic products need the control the pH. Shampoos are there, baby lotions are there, others, washing powder, eye drops, and other laminates are there. Now we start with acidic buffer solution. So you have to give a heading.
Okay. I've copied.
We need a weak acid. Now the word weak acid, why weak acid? Because it's a game of equilibria. This is the name of the chapter. So a buffer solution works like a spring. So spring is an elastic object. Similarly, equilibrium is an elastic system. It can shift right to left and left
Yeah.
to right. Now we have a weak acid, CH3COOH, and you know very well from AS that what is CH3COOH? In our common life, it is vinegar. It is vinegar, and vinegar is obviously, you can see, a weak acid. Some cold drinks also use a derivative of this. Now, a strong acid can't be used as it is fully dissociated. It cannot remove H plus. We see the single arrow. The significance is coming from our idea that this is a single arrow and this is a reversible arrow. We want it to come back. Along with the weak acid, a soluble salt with a common anion must be present. So we make our first buffer, acetic acid, a weak acid, which partially dissociates into CH3, COO minus, and H plus. Then we have a soluble salt and sodium acetate, for example. It has a single arrow, which means it is flooding the ions. So the upper solution is more on the left side. The upper equation is majority on the left side, and the second equation is majority at the right hand side. Now this is the common ion. So after giving the heading, you have to copy this example.
I've copied.
Now assume that by mistake have added an acid in this solution. Acid means you have added a good
H.
amount of H plus. Okay. Now
Yeah.
H plus enter the solution, and H plus will find CH3 COO minus. CH3 COO minus are flooded. They are huge in number. Why they are huge in number? Because they are being transferred by the soluble salt. Now H plus will go and combine with the negative ion. After combining, the second reaction can't reverse, but the first reaction can reverse. So H plus will keep on combining with the CH3 COO minus, and it will be shifting backward. So suppose you have added 100 H plus, all of them will be shifted to the left, and the reaction will come back to the same position as it was before. It is just like H plus entered in the area and they are hunted down by CH3 COO minus, and then they are removed. This is how this buffer is going to fight against H plus. Now, if you add by chance an alkali, alkali means a huge quantity of maybe OH minus. Now, OH minus will have a strong tendency to combine with H plus,
H plus.
and that will form water. There will be a drop in H plus concentration, which will be compensated by the equilibrium to the right. In that,
Yes.
solution will again get the same EH because H plus is returned. So in this way, this system is capable of fighting against the acid and an alkali.
Okay.
So you have to copy this concept map.
Okay. I've copied.
Now the attack of alkali. The equilibrium shift to the right to compensate and the pH regains. You have to copy this concept map.
Okay. I've copied.
Now we have a summary. For an acidic buffer solution, one needs large concentration of acetic acid and large concentration of CH3COO minus. So this will be a summary. You have to copy this.
I've copied.
Alkaline buffer solution. So give this heading now. Now here, this is again a good example, and that sometimes people complain, and everyone has gone through these experiences if they have a chance of taking antibiotics or other medicines. So people complain that they have lost the taste of their mouth. Some people feel acidic problems, some people feel acidity. Now, these are all the disturbance we cause in the buffer systems. Nature has established number of buffers within us and outside us. These buffers are actually now we believe that they are actually surrounding us. So this buffer is an equilibrium. Now this concept should be clear that it is not like a ever resisting system. If you keep on adding the acid, obviously the equilibrium will break. That is why I gave the example it as a spring. So if you understand this example, then two results can be made. One, buffer solution is not that which doesn't allow the change of pH. It allows the change. Obviously, it's like a spring, it compresses, but then it tries to return like a balance, like a beam balance. If you disturb it, it comes back. And you remember that, hopefully, that was the key example for understanding Le Chatelier principle.
Yes.
So that is a very important point. It means that the pH is not like a reflector. Buffer solution is not a reflector. It will undergo a change in pH. That is why medicines are not always injected in the blood. This is normally in many stable areas. We do not go for this as the first choice. Until the situation is critical, we go for the mouth and we observe that, so that if there is any problem, reaction, issue, we can resolve it, because blood is the last station. Similarly, the second concept is necessary to understand that pH is not an ultimate shield. It is there like a spring. If you keep on pressing the spring, it will deform like this buffer, it will break. So I have to copy now alkaline buffer. It is very similar, but is based on the equilibrium surrounding a weak base. The famous name is ammonia. And you have to copy this.
Okay.
Ammonia in water is forming a weak solution.
I've copied.
So very similar, but is based on the equilibrium surrounding. Ammonia was in our AS also. Ammonia is famous for its very high solubility in water, and we say that ammonia is soluble in water in every proportion. So ammonia is a very soluble gas. We need a large concentration of OH minus to react with any H plus, large concentration of ammonium ion to react with any OH. So you understand here that NH4 will take up OH minus, and OH minus, as there before, will take up the H plus. Now, if there is enough ammonia to act as a source of OH, but one needs to increase the concentration of ammonium ion by adding an ammonium salt, because obviously ammonia is a weak alkali. Ammonia itself cannot generate much NH4 plus because they have to fight with OH minus. So we make a solution of this one. This is the idea of our buffer. So now you have to see this ammonium ion. You have already copied the first equation. So below it, you have to copy the second equation.
Okay. I've copied.
This is the common ion. You have to copy this, make it common. I mean.
Okay.
So here we need a flooding of ammonium ion, and that is possible from a soluble salt.
Yes.
Now this is a solution. You identify hopefully H3O plus, our old friend. H3O plus is called oxonium ion. And when it is formed, when H plus react with H2O.
Yes.
Now, we have added a soluble salt. I'm going to add acid. No, sorry. So this is not good. Unfortunately, it's not working. Technology is a misery. So, fail. So,
a buffer is an aqueous solution containing both a weak acid and a weak base that are a conjugate acid-base pair. The buffer shown contains the weak acid acetic acid and its conjugate base acetate. These species are dissolved in water. Water molecules are not shown in this animation to draw focus to the buffer components. A buffer solution has the ability to resist changes in pH upon the addition of small amounts of either acid or base. Choose to add a strong acid or a strong base to the buffer by clicking one of the buttons. Only hydrogen ions, H+, from the hydrochloric acid are shown entering the solution. Chloride is not shown because it is a spectator ion. It does not participate in the reaction. The strong acid H+ reacts with the base component of the buffer acetate, CH3COO-, producing the acid component of the buffer acetic acid, CH3COOH. The buffer has resisted a change in pH by removing strong acid, H+, from the solution. Only hydroxide ions, OH-, from the strong base sodium hydroxide are shown entering the solution. Sodium ions are not shown because they are spectator ions. They do not participate in the reaction. The strong base hydroxide, OH-, reacts with the acid component of the buffer acetic acid, CH3COOH, producing the base component of the buffer acetate, CH3COO-, and water. This buffer has resisted a change in pH by removing the strong base hydroxide from the solution.
Calculation of pH of buffer solution, and we are starting with an acid buffer and with a soluble salt for single arrow, and I have made the Ka the dissociation constant. You have to copy this.
Okay. I've copied.
Ha is concentration of Ha acid. A minus is the concentration of A minus from Ma. The amount of A minus for Ha is very small, can be ignored. So we rearrange the equation and we made H plus the subject. This is a formula which can be used to manage the H plus concentration. You have to copy this derivation further.
Okay. I've copied.
We can write it like this, assuming Ha is the acid and A minus is coming from the salt. H plus is Ka. Now, this is a virtual step needed, and that is not actually required directly. So let's leave the log step and copy this because you're not taking maths. So you have to copy this equation first.
I've copied.
Now you have to copy the formula for pH of a buffer solution.
Okay.
There are not two formulas. There is only one formula. but only for the difference of the ratio, fraction, the sign changes. This is a property of log.
Okay. I've copied.
So this equation is mathematical equation, and we can write it in different formats. This equation explains why the pH is affected very little by dilution, because the ratio of acid to salt remains constant on dilution. So we take an example here. Calculate the pH of a buffer. You have to copy this question.
Okay. I've copied.
Now we have the Ka value, and we have the Ka, we have the acid, we have the salt, and we need to find the pH. The data, you have to copy the data and put them in the formula.
Yes. I'm getting 2 times 10 to the power of -4 again.
For what? For pH? No.
Yes.
How pH can be in terms of power?
1 second.
I've shown the steps.
Okay, yes, I got 3.6.
Because pH can't be in power of something, because actually we get log to remove the power of 10.
Yes.
So that is all. We have completed the buffer, and that was the main topic of this chapter. We have another topic which they added in 2016, partition coefficient, but it is not the core topic. But anyways, we will inshallah continue in our next class.
Inshallah. Thank you.